Hey guys, so today we are gonna take a look at buffer overflows in Windows. This is mainly prep for OSCP to help some of my friends out. They asked me to put a guide together, so I wanted to share this guide with the rest of the world. So I've created a document of a guide with some like Python shell code, and then a bunch of steps to carry out to basically get all the way through a buffer overflow. And we are going to go through that today, and hopefully it'll all work. To do this, we're going to be using TryHackMe. There's a buffer overflow prep room, and there's a VM in here that basically has 10 different overflows that we can mess around with and try and see if we can get our code to work. So first things first is we grab the IP address, head over to our Kali machine, and we want to our desktop into the Windows machine. We want to go to other user, and the credentials for this box is admin and password. Once that puts up, we can start getting things into order. So I've created a YouTube Overflow 2 room. Increase the font size so you guys can see everything we need, and let's create our Python code using Sublime, and we can go to our notes and copy our base shell code in. So we just have a bunch of info here, things that we should keep track of, and then we've got all our buffer variables that we can edit and change, and then the actual shell code, exploit code itself. So let us go into the Windows machine and start up the application. We're going to start up Immunity Debugger, which is what we're going to see the memory values and allow us to find return addresses and things like that. Go File, Open, and we go back to the desktop. Sorry, users admin desktop, vulnerable apps, OSCP, and run OSCP application. We can change the appearance so it makes it slightly easier for you guys on YouTube to see. So we will make it 16, I believe, is a good size. I don't know why it went to terminal 6. We want font 7, 16. Okay. Okay, cool. So that makes it a bit more clear. So Immunity, we have a bit of things. We have the addresses and the modules on the left with all the commands. The NASM script and the actual machine language, so jumps, calls, moves, etc. We have a hex dump down the bottom left. We have all our registers on the top right side, and we have the next address used to be executed on the bottom right. So these are all the addresses that will be run next. So first things first is step 1 is to just play with the actual application itself. So we're going to use netcat to connect to not type the code. So let's grab this IP address again. And netcat. And the IP address and port 1337. We have the application paused, so we hit this little red play button to run the play, and now the application is running. So when you load an application in Immunity, it starts paused. You have to hit that little red button to play. So if you get issues connecting to the box or things, that is usually what the issue is. Or it might be a network issue, you need to be on the VPN for TryHackMe. So we have our application here, and we can see there's a prefix that we have to enter, so overflow 2, and we can basically put in a value and it'll basically be complete. So what we could do from here is we could go and put in manual and try and crash it manually, or we can use a little bit of Python code to print out a bunch of A's for us. So if we go back to our guide, we have the code here. So Python C print A times 1000, and we now have 1000 A's that we can copy, and we go to overflow 2 and paste those 1000 A's, hit enter, try help again. We don't get the overflow 2 complete, and we don't get the help, so we have successfully crashed the application. If we look, we can now see that all the registers are filled with A's. The application has now paused, so it's now in a crashed state basically. So 1000 has definitely crashed this application. So if we restart the application by pressing those two black back arrows, we can run the application again. We can now look into our Python code. So we know the software name is called OSCP. We know the vulnerable input is overflow 2. We have the target IP as 10.10.97.122. And we know the proof of concept crash length is now 1000. So the next thing for us to do is get this Python code working and making sure that we can replicate this crash using Python. And I always say to try and get one step working 100% before moving on and trying to jump the gun, purely because if you go 3 steps in and then nothing works, you have to debug 3 steps. Whereas if we work at each step perfectly, then we know where to debug better. So we need to change our buffer slightly because there is a prefix on this machine. We need to send this prefix of overflow 2 and then a space and then our A's. At the moment, all this application, all this Python code will do is send 1000 A's at whatever it is. So we'd never hit that trigger. So we can create a new variable here called prefix, and we can just call this overflow 2. And then when we come down to our buffer on the exploit code, we can now send prefix. We can then put a space in to basically send the prefix, a space, and then our 1000 A's. So we can hit F7 to try this and run. And there's an error. Why is there an error? I didn't save it. So yep, Control S to save, F7 to run, and we can see that our application has crashed again with all these A's. So we can try this again just to triple check. Hit play, F7 on our code, go back, and yeah, it's gone into a crash state. Access violation when executing 41, 41, 41. We know 41 is the hex value of the ASCII character A. So we can see all the A's here. So the next step is to find the offset value. So to do this, we can either use a web application to do this, or we can use a tool within Kali. I quite like just to use the tool in Kali because it's simple and I know it works. So we put a length of 1000, and what this does is creates a unique string of unique characters all the way through for as long as we want. So you can see it's A0, AA0, AA1, AA2. This would go all the way through to Z's. So it can be, huge numbers. We can copy this, go back to our Python code. And now instead of fuzz, we can send that string and comment out the rest of the string. So fuzz will now just send this unique string through. So we can save this, check our application is running, which it is. F7 to send the evil buffer, and we have now got a crash. What we do is we come to this EIP register here, and we can copy this selection, and we can just take a note of it for 2 seconds. And we can then go and use the other tool, the pattern offset Ruby script. and we can put that value in with a -q for the query. And this now gives us an offset of C634. So we make a note of this offset. We can make it up here. And we can also put in it into a variable as well. So the next step is we can now remove the fuzz string. And we can now go back to printing our A's. But instead of 1,000 A's this time, we want to send the offset amount of A's. Then we want to send B's. And there are 4 bytes within EIP. So this is us trying to control that EIP register. So we want to send 4 B's. And then we can send a bunch of C's afterwards. Now, in realistic terms, what you should do is you should send the amount of C's to start with is your initial proof of concept length crash, and then -4 and minus the offset. And then that leaves you still with your 1,000 characters of A's, B's, and C's. So C is the value 1,000 minus the 4 B's and minus all the A's. It's good practice to get into this. What we do then is we can restart the application, make sure it's running, and run our code. Okay, so we get to, once we've sent this in, we now see that the application has crashed with 42, 42, 42, 42, which is the hex for B's, and we have all our C's in the next, and ESP, which is the next instructions to be read. So we send all our A's, and then the 4 B's, and then all the C's, and our B's are in EIP. So this is perfect. We now have control over EIP, which is the register, the instruction pointer. So this is the register that we want to take control of. So once we have found the offset and we have managed to control EIP, the next step is to try and increase the number of C's. So we need 350 characters for remote access Trojan, minimum. But ideally we want as much room as we can to play. So the quickest and easiest way to do this is literally just increase this to 2,000 and test it. We need to make sure that the application is running. We have 7, check it, and all the C's have gone in. Okay, cool. So we've been able to increase our payload spacing. So where those C's are, we're going to obviously put our payload in there at the end. So it's good that we can do that and get those in. So what's next? We need to find bad characters. So bad characters is a string all the way from 00 all the way to FF. 00 stands for null byte, so it'll always be a bad character. But we basically just want a string now of 01 to FF that we can pump into the application. And there's a Python script here to generate this string as well. So we can go back to our Python code and we can go to bad characters here. We are going to need to move it just above the fuzz, and we then send, instead of the C's, we send bad cars instead, and we can comment out the rest of this line. So now we send our A times the offset, the 4 B's, and then a bunch of bad characters. We can save this and we can run it, make sure the application is running. Application is running. Okay, F7 and come in, find ESP where that string should now start. So we can see EIP is 42, 42, so ESP should be our 1, 2, 3, 4s, the unique string. And you can see our hex dump now has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, it goes 0A, 0B, 0C, 0D, 0E. 0f. We follow this through, making sure that it's all in the sequence up until we see an error. So 1E, 1F, 20, 21, 22, 0A. So we expect 23 here, not 0A. So 23 is a bad character. So we can then restart the application, come back to our Python code, record that 23 is a bad character, and remove it from this string. So we remove 23 from the bad character string. We save, and we hit F7 and run it again, and we carry on from where we left off. So we follow ESP in the dump, go through it to 23, so 22, 24, because we've moved 23, 25, 26, 27, 28, 29, 2A, 2B, 2C, 2D, 2E, 2F. So this is counting in hex. And we can follow this through now, all the way through to the next. Next bad character, which looks to be 3C. So it'd be 3A, 3B, 3C. So once again, we can come here. We can make a note of 3C, go into our string, and remove 3C. Save, make sure the application is running, and run our code again. And we just rinse and repeat this until we have found all the bad characters. So here's the next one, 8.3. Make a note of 8.3. Find 8.3 in our string and remove it. Save. Check the application is running. It is. Run our code again. Follow ESP in the dump. And we got to 8.3, so 8.1.2, and keep going through. All the way to FF. At FF, we have finished the string, so we no longer need to go through it. So once we hit FF, end of the bad characters. So once we've discovered all our bad characters, we can now move on to the next step, which is going to be redirecting execution. So unfortunately, we have EIP when we put our 4Bs in EIP. But what we want to do is then go straight into ESP. Now these addresses here in these registers change all the time. Every time the application starts, every time the application crashes, these registers all crash. The addresses all change for these registers. So telling EIP to go straight to ESP just will not work. We can't use this address to say this is the next address to go to, because this address changes all the time. So what we need to do is we need to find a command in the program or in the .dll that the program's using that is a jump, and then it jumps to the ESP register. So how we do this is we can use a monoscript. So down at the very bottom of immunity, we can put an exclamation mark Mona, jump to ESP, and then the -b is bad characters. The reason why we put bad characters here is because we know these bad characters do funky things with the application. So we do not want these bad characters appearing within the address of the address we're using. So we hit go, and you saw green text appear there and then disappear. To get that back up, we go to Window and Log Data, and you can see the output of the script here. Number of pointers of type jump ESP, there are 9. And these are the addresses at the front here. So what we're mainly looking for is ASLR being false, ideally all of them being false, because these are all stack protections to try and stop us doing buffer overflows. So I'm just going to take the top one here. So we can copy to clipboard and copy the address. It's in the ESS function.dll, this command, and ASLR is false. So we can now come back to our code and put in the address here, which is the jump ESP address. And now what we need to look at is a little endian, the endianness of the system. So I believe this is a 32-bit system. So we are running, Windows 7 Professional 32-bit, and I believe the application is using little endian. So the main thing being that you have, if it's little endian, it fills the stack up from the bottom to the top from our address, and if it's a big endian system, it will fill the memory from the top to the bottom. So what this means is we have to convert the address into little endian. We have to flip it around to be backwards. So the easiest way to do this is look at this address and type the 2 characters at the back, then the 2, 11, then the 50, then the 62. So we have AF, then 11, then 50, then 62. We then can turn these into hex characters and copy this and put this in our return variable, and we'll need to make it a string. Cool. So at this point it's worth tidying up our code a little bit, so we can comment out bad characters as we no longer need it. We can bring back our C's. We will need to move our return address above the fuzz variable, because we're going to be calling that return address within the fuzz variable. And now instead of these 4 B's, we want to call the return variable. So this is now going to do the 634 A's from the offset. It's then going to put in the return address of what we just worked out in little endian format, and then it's going to put our C's. So what we want to do is double check that our jump ESP address is working and going to where we actually want it to go. So we can go back to our program, restart it, make sure it's running, and then we can press these 4 black dots with the arrow to go to an expression, enter the address in the format we found it in, not the little endian format, the format appears. Hit OK, and we go to this address, which is the jump ESP. And we press F2 to put a breakpoint on, which will turn the address teal blue. We can then run our code, and it now hits this breakpoint. So what we can see at this breakpoint, when the program hits the breakpoint, we can see that the address 625011AF, which is this jump ESP, is an EIP, the instruction pointer. And ESP is 018CFA30, which down here we can see is our C's. So if we were to step into this, which is this one, we can either press this red arrow with the 4 dots, or we can press F7. We can then see the code starts jumping through these 43s, which is all the C's. So we now have redirection, we have full control over EIP, and we have redirection of EIP into ESP, which is exactly what we want. So once we are here, we can now start creating our payload. So in Kali, what we do is we use MSF Venom, and we want a Windows shell reverse TCP for this case. It's a basic reverse TCP shell. We use ton 0 because we're using the VPN, so our local host IP is going to be ton 0. Our local port is going to be 4444. If sometimes there's firewalls on the systems, we might want to change this to 443 or a common port that a firewall might not be blocking. The architecture of the system is 86, so 32-bit system. The platform is Windows. Our bad characters we need to change. Actually, I believe those are the same bad characters. So yeah, we'd put our bad characters in here. And then we encode the payload with Shikata GANI, which is an XOR polymorphic encoder. And then we output this file as a Python file. Let's just double check these bad characters, 23.3c83, 23.3c83, XBA, yep. So we hit enter. This will generate our payload. Cannot find the payload. I always get the encoder mixed up. So there we go. It's Shikata Nagai. We can then copy this buff variable into our code. And the B in Python puts it in as bytes. For this particular one, we do not want it to go in as bytes, so we can remove all these B's. We just want it to go in as a string. And we can now build our final exploit. So our buffer is going to be the prefix plus a space plus fuzz, which our fuzz variable contains the offset plus the return. So we can now comment that out. So all we want fuzz to do is a plus the offset. We then, after those a's, we want the return variable, which is our return address. And then we want buff, which is our buffer. So this new variable here, buffer. The very, very final thing to do is nops. So there are nop instructions, which are represented as hex 90, and this just presents some space for our payload to decode itself, basically. Because we've encoded it, we want to grant it some space to decode it. So we can come back to our Python code, and we can now comment out this padding line, and we can put in the hex character for a nop, which is /x90, and we'll just put 16 of these in. And then we want the padding between the return address and our buffer, so we put our variable here. And if everything goes well and smooth, we can now start up a listener on port 4444. So this is now listening for any incoming connections. We can then make sure the application is running, and we can execute our code. So we check our payload, and we have found that I was right the first time, it's Shikata GANI, but I never actually read, and it cannot find a way to permutate with these bad characters without using one of these bad characters. So for this particular one, the best thing to do is just remove the encoding. We use encoding to get past antivirus and things. We can then take this buffer, go in and replace our buff code. Remove all these B's again. Hit save. Make sure the application is running. Make sure our listener is running. And we can now run our code. And we now have a shell. So we can see we are now on the box as an admin user. So the IP 10.10.97122 matches our try-hack-me address. So I hope you learned something. I'm gonna put this guide in the about section, so feel free to check it out. If there's any errors or issues, let me know. But yeah, please comment, like, subscribe. I will try and get back to you. You can also catch me on Twitch, where I'm doing a lot of this stuff live, so you can interact and ask a bunch of questions. But thank you very much.